So when I am working with a second order differential equation, let's make our life easy. We'll make it linear and homogeneous. So that's L of y equals A2 of x, y double prime, plus A1 of x, y prime, plus A0x, y. And I'm working with L of y equals 0. That's what the homogeneous part means. I need to find the functions that form a fundamental set. Now, I know this is going to sound ass backwards for a minute, but I'm going to start with the assumption that I have one of the solutions, not both of them. We will eventually find methods for finding the first one, but I want to start with the idea I've got one, how do I get another one? The advantage is that we've used this technique idea before. I'm going to do some messing around and turn my second degree equation into a first degree equation. This only works if I know that the two functions I'm going to end up with are part of a fundamental set of solutions. What's the big deal about being part of a fundamental set from yesterday? Yes. And if the determinant is not 0, those functions are, what's the adjective? They're independent. So that means that one of them isn't a multiple of the other. Because if the Wronskian were to have turned out to be 0, then when I do a linear combination, I'll get 0 with some constant in there. So if they're independent, I can't do that. They must be non-constant related. All right. So these are both functions of x, which means if that's not a constant, I get another function of x. I don't know what this u is, but it's some other function. Well, if that's true, then I can write y2 as u times y1, where both of those are functions. Ah, if I can now work with this expression in the differential equation, then maybe I can solve for u. And if I find u, then I find y2. Maybe, hopefully, as long as everything works out nice. The hope is that when I plug this expression in to my differential equation, nice things happen. So rather than me just flap my lips, let's do an example. So my first question is the function y equals e to the 2x a solution to this differential equation? We should check. First derivative is, second derivative is, and when I plug that in, I have 4e to the 2x minus 4 times 2e to the 2x plus 4e to the 2x. That's plus 4 minus 8. That is 0. Great. I want another equation. I want y2. I want it to be independent. So I'm going to use this substitution, this trick that I hope will reduce my order. So let's assume that y2 is something times e to the 2x, where u is some function. I need you to do the first and second derivatives of y2. U is a function. Since u is a function, I have to do the product rule. Derivative of u is u prime. Then I leave the e to the 2x. Then I leave the u alone, and I get 2e to the 2x. It might be worthwhile to refactor this, to separate and regroup. I don't know, pull out an e to the 2x. I'm going to leave it just like this. I don't need to deal with that at the moment. But I need the second derivative, y2 double prime. I do the derivative here, I get u double prime, leaving the e to the 2x alone. Then I do the e to the 2x, leaving the u prime. Then this pair, I do the u. Wait, that becomes the u prime. Hey, look at that. Leave the 2e to the 2x alone. Plus u, do the derivative of this, 4e to the 2x. I am going to put those together. U double prime e to the 2x plus 4 e to the 2x u prime plus 4 e to the 2x u. This is getting gross. So now let's take all this garbage and plug it in to our differential equation. Let's see what happens. Y double prime, that's all of this. Oop, that's a minus sign. No, it's plus sign. Never mind. U prime, U plus. Oh, there's the minus sign. Minus 4 times Y prime. U prime e to the 2x plus U2 e to the 2x plus 4y. Bleh, right? All right, hang on a second. I got a bunch of U prime terms. I got a bunch of U terms. Let's group those. The only U double prime term has an e to the 2x in it. Right here. The U prime terms, 1, 2. Hey, what happens there? Yay, that's a 0. Plus U terms. Well, I got a 4e to the 2x up here. I got a minus 8e to the 2x from here. Oh, and then I have this plus 4 right here. What happens? That also cancels out. But this was our differential equation to start with, right? And we want this to be equal to 0. It was a homogeneous equation. Well, that means that U double prime e to the 2x is equal to 0. Can e to the 2x ever be 0? Well, that means U double prime is 0. If U double prime is 0, what's U? What's the integral of 0?
Oh, integral.
I mean, yeah, I hit somebody with that every semester. No, don't worry about it. The integral of 0 is constant. But this is the second derivative, right? So U prime is a constant. What's U? Cx, because this is a function of x. I'm integrating with respect to x. Wait a minute. There's no reason for me to pick any particular constant. I might as well just let it be 1. Without loss of generality, assume the constant is 1. Then U is just x. Wait a minute. Where was I using U? All the way back up the top of this page. Right there. So y2 is x e to the x. And that is a second solution to my differential equation. I claim. Is this a solution to y double prime minus 4y prime plus 4y equals 0? Let's check. I need the first and second derivatives of x e to the x. Oh, wait a second. I made a typo. Yeah, I forgot the 2. There's a 2 up there. Can't forget the 2. It was in the original problem. Can't lose it.
E to 2x plus 2x.
And this time I will simplify it by factoring out the e to the 2x. And then y double prime, the derivative of this is 2 e to the 2x plus, leave the 1 plus 2x alone. The derivative of that is 2 e to the 2x. So I get 2 plus, oh, there's 3 of them. 2, I can add 4. There's 2 e to the 2x here. There's 2 more e to the 2x there, plus 4x e to the 2x on the outside. Plug it in, see if everything cancels out. Y double prime minus 4y prime plus 4y equals, I got 4 minus 4. I can factor out the e to the 2x out of everything. 4 plus 4x minus 4 minus 8x plus 4x. What happens there? Four minus 4, 4x plus 4x minus 8x. Poof. I found a second solution. Given one, I was able to build another. Say again? Oh boy. There's one other thing I should check. I want these solutions to form a fundamental set. Want them to be independent. The way to check independence is to check the Wronskian. I write the equations in the first line. I write their derivatives in the second line. But I already worked out the first derivative of y2 up there. So I have it. I don't have to recalculate it. If you want, we can just plug in a number, or we can take the derivative, the determinant as is, and I get 1 plus 2x times e to the 4x minus 2x e to the 4x. Well, the 2x e to the 4x cancels. I'm just left with e to the 4x, which is never equal to 0. So my equations, y1 and y2, form a fundamental set of solutions. We did it. Whew. Now, I actually went a little overboard on this particular problem because I checked everything. I checked that I was giving you a solution in the first place. If you have some trust in me, then you don't have to check that part. but I can lie my ass off, so you probably should. I built this to be an independent solution. That means it should be a solution, but we checked anyway, and it should be independent, but we checked anyway. As long as I have one solution, I can build the second one. As long as I go through this process of reducing my complicated differential equation, which involved second derivatives and original functions, to something much simpler. In this case, u double prime equals 0. It was a really easy problem to solve, wasn't it? Once I fixed it with this trick. I forgot to say that every solution has an interval. In this case, the interval is minus infinity to infinity. Let's try it again. I claim x to the fourth is a solution. I want you to find me an independent second solution. You have time. Go for it. I'm making the assumption that I actually did give you a solution, so I'm not checking it. So I write y equals u times y1, then I start my product rule derivatives. So now that I have y2 double prime, y2 prime, and y2, I can plug those back in up here. X squared times y double prime. Minus 7x times y prime plus 16 times the original should be 0. A large amount of regrouping in algebra. I have x to the 6th u double prime plus 8x to the 5th u prime plus 12x to the 4th u minus 7x to the 5th u prime minus 28 x cubed, x to the 4th, because there's an extra x out there, u, plus 16 u x to the 4th. That should equal 0. Wait a minute. X to the 4th u, x to the 4th u, x to the 4th u, what happens there? That gives me a 0. Plus 12 plus 16 minus 28. So that means I have x to the 6th u double prime minus 7x to the 5th u prime. Oh, wait a minute. Minus 7 plus 8. That just becomes plus 1. Hang on a second. I only have u double prime and u prime. I'm only looking at a function and its first derivative. I'm looking at the function u prime and its first derivative, u double prime. Out comes a change of variable. I'm going to let v equal u prime. Then this equation becomes x to the 6th v prime plus x to the 5th v equals 0. This is first order, linear, and homogeneous. But it's first order and linear. I know how to solve those. That was last exam. How do I solve this?
Oh. These. Or that's not.
That's not this version.
That's not what-
Right. As a matter of fact, let me just go with this as first order and linear. Linear. Let's ignore the homogeneous part for the moment. Because when I think of homogeneous like that, it's got to have a dx and a dy. And this doesn't have that set up at the moment. I know what it's called, but what do you know what it's called? Grab the formula sheet from the first exam. Because you wrote notes.
X.
Well, that would, again, if I had a dx and a dy, I'd have that set up.
Seven.
I need an integrating factor. This is linear.
Yes.
Linear, I need that. But in order to do that, I need the first derivative to be alone. So I divide everything by the x to the 6th. And there's my integrating factor set up. Everything but. This is why we write formula sheets, Noah. I don't expect you to have this crap memorized. I'm cheating. I have done this course 8 times, 9 times, a lot. And I keep teaching this stuff, the same idea in multiple cases. You've been doing this not even 6 weeks. What's my integrating factor? Right, because I'm going to do e to the integral 1 over x dx. That's e to the ln of x, which is just x. So my integrating factor, when I multiply through, I get x v prime plus 1v equals 0. But that means that the left-hand side is x v quantity prime. That's a product rule derivative. That's equal to 0. So what happens? Xv equals a constant because I integrate on both sides. And that means that v is number over x. Again, without any loss of generality, I'm going to let that constant be 1. Wait a minute, that's v. Where the hell did v come from again? V is u prime. U prime is 1 over x. What's u? Ln of x. And that means that I now know y2. What is my second independent solution? Because of the way I don't write parentheses around my ln's, I tend to put the stuff that's not in the ln in front instead of in back. One of my personal peccadillos. There you go. Notice my first solution and my second solution. That gives me a fundamental set on the interval that I specified at the beginning of this problem. On I equals 0 to infinity. Why did I need to avoid 0? Why is this the right interval? Can't take an ln of 0. I can't take the logarithm of a negative number. As a matter of fact, when we set this problem up at the very beginning, we have x squared times y double prime. When we think of a normal differential equation, the first thing we want to do is divide out that leading coefficient, which means we are dividing by x squared. I can't have x being 0. We'd either be on x bigger than 0 or x smaller than 0. If I was on x smaller than 0, I would have to have absolute values in all of my logarithms. All right. If I really want to be pedantic about this, what I'm doing is a double integrating factor. This technique that we just did with the integrating factor, e to the integral of p of x, that's exactly the right idea. I just have to do it more than once. So if I do what I was just talking about and divide out that first coefficient, it turns out we can actually go through this entire process like it was an integrating factor problem. But we end up doing that integration twice. Because we reduced the order, that's where we got v from. And then we have to integrate again to get u. And we have to multiply it on. Now remember, this said I was going to start with the assumption that we have a solution. It turns out we get y2 of x is y1 of x times u. But because we've rewritten this to look like this, u always has the same form. It's an integral inside an integral. This formula appears on page 133. And I'm going to tell you right now, I hate this formula. Absolutely despise it. But let's go back and look at our previous example, the one we just finished. Let's go back to the very beginning of that differential equation. It was x squared y double prime minus 7x y prime plus 16y equals 0. I'm going to divide by the x squared. Y double prime minus 7 over x y prime plus 16 over x squared y equals 0. There's my p of x next to the y prime right there. And we said that we had a solution. y1 was x to the fourth. Ready for the fun? Me neither. y2 equals, according to this, x to the fourth times the integral of e to the negative integral p of x minus 7 over x dx all over y1 squared, x to the fourth squared, integrate with respect to x again. X to the fourth. What is the integral of 7, negative 7? Wait a minute, there's a negative inside and a negative outside, right? They cancel. E to the integral 7 over x dx over x to the 8th dx. What's the integral of 7 over x? Okay. So it becomes e to the and then those e and ln cancel, and I just get x to the 7th. So now this is x to the 4th times the integral of x to the 7th over x to the 8th dx. Which is x to the 4th times the integral 1 over x dx. What's the integral 1 over x? Lo and behold, I get x to the 4th ln of x. Exactly the same result. Okay, so let me ask you the stupid question.
Why the hell didn't you just go to the formula in the first place?
First of all, because I can't remember this formula to save my ass. But I can always remember the substitution I want is u equals y over x, right? y2 over y1. It's the same setup as my homogeneous equation idea. I take one function over the other. That's where I started this game. I said the thing to do is to write the substitution. And that's the same substitution we used a chapter ago. So if I can remember to do the same thing, just do a bunch more algebra, rather than try and jam another really complicated looking formula into my head, I'd rather do that. Most of the time. And I mean this literally, most of the time, I'd rather do the whole problem out the long way. But if I write y2 equals u plus the quantity 1 times x, and then I go back in and do all this algebra, I've got about 2 pages of algebra waiting. Now, mind you, it's algebra. So it's not difficult, it's just tedious. Well, F that, let's go directly to the formula. If I divide by this, I have y double prime plus 2 times the quantity 1 plus x over 1 minus 2x minus x squared y prime minus 2 over the quantity 1 minus 2x minus x squared y equals 0. Here is p of x. The formula for y2 is going to require me to do e to the integral negative p of x dx. So let's just start there. I know that's in the formula because the formula had that inside integral and then the outside integral, right? So I got to do this part first. Let's go ahead and do that part first. All right, I'm just going to write y2 needs this integral. So let's work out this integral. That's e to the negative integral 2 parentheses 1 plus x over 1 minus 2x minus x squared dx. I promise this integral is easier than you think it is. Let's do that. Now what? What was that, Jim? No, I actually think it's the right thing to do.
Distribute or factor. So.
Yeah, the derivative of this is minus 2x, isn't it? So if I do u is 1 minus 2x minus x squared, then du is negative 2 minus 2x, and that's exactly what we have on the top. That makes this e to the integral 1 over u du. What's that? Hey, e to the ln of u, the e and the ln cancel, that's just u. So I get 1 minus 2x minus x squared. Now, the formula says y2 is y1 times e to the negative integral p of x dx over y1 squared dx. We just worked out the top. The top is this. Ah. I don't like it. Hey, hang on a second. What's 1 plus x all squared?
Oh, so that's.
The only difference between this and this is the signs, right? 2 minus 1 plus x quantity squared would be 2 minus 1 plus 2x plus x squared. Two minus 1 is 1. Distribute the minus. Distribute the minus. The top of this fraction can be written nicely. Why would I do that? Because now I split this up into two separate fractions, and I get 2 over 1 plus x squared minus 1. What's the integral of 1? That's the easy part. How do I do this integral? Again, this is one that's easier than you think it is. I'm sorry? No, actually, if I break it up, it's just going to come right back to this, unfortunately. If I try and do partial fractions, I'm just going to get right back here. If I do u equals 1 plus x, then du is 1. So this becomes the integral of 2 over u du squared. Sorry, 2 over u squared. Got to write the right numbers in. Wait a minute. What's the integral of 2u to the negative 2. So I get negative 2 over 1 plus x. Negative 2 over u. Bingo. Multiply through. You get negative 2 minus x times the quantity 1 plus x, or negative 2 minus x squared. Here's y2. We found it. Jumping right to the formula. Still took me 2 freaking pages of work. Did it save me any time? Not a damn bit. So as much as I know having this formula is a useful thing, I'd rather do the damn algebra. I like algebra. Algebra's easy. I can do algebra. By the way, you'll notice every number in here is multiplied by a negative 1, right? I can always fudge a constant. So it's no different for me to say 2 plus x squared. Because my general solution is c1y1 plus c2y2. And that means that I'd have some constant in front of that anyway. Whether it's a positive or a negative is irrelevant. Questions? I'm the first guy to tell you, hey, you have a formula, you should write it down on your formula sheet right now. The formula sheet for your next exam should have this formula on it. I'm not sure I like using it, but you should have it. Somebody asked me a question. Actually, my brother gave me this one. It's Hawaii original. The reason I don't like using the formula is because the formula only works for homogeneous equations. The process works even if it's not homogeneous. Here is the same idea. Only instead of being 0 on the right, oh, that should be e to the negative 2x. I want to solve this where it's equal to 2. By the way, I just picked a number because it's easy. You could pick any expression you want. You could pick e to the x, e to the 2x. You could pick sine of x, cosine of x. We could pick all sorts of stuff over there. I'm just going to use 2 for the moment to show you that the idea still works. Even if I don't know my second solution. I can't use that formula because the formula only works when it's equal to 0. I can still do the reduction of order substitution. And that would be that y2 is equal to u e to the minus 2x. And then I have to figure out what u is. By the way, I will find the corresponding particular solution for the non-homogeneous part along the way for free. What is y2 prime and y2 double prime? Perfect. Second derivative, I gotta do the product rule twice. U double prime e to the minus 2x minus u prime times 2 e to the negative 2x, the minus sign. Then here, the u becomes a u prime. And I do the second derivative again. The u stays there. I'm going to get a plus 4 e to the 2x, right? With a u. Or does that minus carry through? Wait a minute, I'm losing track. No, that's right. So plug that into here. What happens? What happens immediately before I do anything else in terms with the u's in them? Those cancel. So I'm left with u double prime e to the minus 2x minus 4u prime e to the minus 2x equals 2. Let's get rid of the e to the minus 2x. Let's divide by it. That would give me u double prime minus 4u prime equals 2e to the positive 2x.
Use the original.
Hey, wait a second. I only have a function u prime and its derivative u double prime, just like last time. This is reduced order. This is a linear differential equation. It's not homogeneous, but it is linear. And if it's first order and linear, I need an integrating factor. My integrating factor, mu of x. Well, there's my p of x, the -4, so I integrate that, and I get e to the minus 4x, multiply through e to the minus 4x v prime minus 4 e to the minus 4x v equals 2 e to the negative 2x, because I multiplied by e to the minus 4x. Left side's a product rule. E to the minus 4x times v, quantity prime, 2e to the minus 2x. Now work your way back to y2. E to the minus 4x v is equal to, what's the integral on the right-hand side? Right, but what's that integral? Can't forget my plus c. So that means v, divide this out, that gives me minus e to the 2x plus c e to the 4x. So far, so good? But that's v. V is u prime. That's plus. Don't screw that up, Josh. That's plus. E to the 2x plus c e to the 4x dx. Integrate again, and you get... This one tight? That's positive 2, not a negative 2.
Positive.
Yeah.
That's negative. Two x plus cx. Oh, no. What did we do with the constant?
Well, I do, let's ignore it. Let's leave it there. What's the integral of e to the 4x? Plus another constant, right? Great. I'm perfectly happy with this. By the way, you are absolutely welcome to let this constant be a 0 if you want. But let me show you why. We're going to leave it there for now. That's u. What's y2? I said we have to work our way all the way back to y2. What's y2? Not using the formula, I'm just using the substitution. It's u times e to the minus 2x. With me so far? I'm going to multiply that through, and I get -1/2 plus c over 4 e to the positive 2x plus d e to the negative 2x. What was y1 again? Aren't those the same part? Number times e to the 2x, right? Negative 2x. That's why I can let this d be constant, because this piece is already covered by y1. Please notice that means my general solution, c1 e to the minus 2x, plus some other constant, e to the positive 2x, minus 1/2. Hey, wait a minute. This is my YC, my corresponding homogeneous solution. This is the particular solution for this non-homogeneous equation. I don't need that double integral inside an integral formula as long as I can do the algebra involved in getting here. And then it works in a broader case of problems. It's more general, which is why having the formula is nice, but I can't memorize formulas to save my ass. I can remember procedures. And the procedure for reduction of order is to take the solution we have, multiply by something, and then solve for the something. Now, the $64,000 question is, where the hell do I come up with the first solution in the first place? That's what we'll pick up on tomorrow. All right? Have a wonderful rest of your day, people. I will see you tomorrow.